Ever since grade school, you've probably learned about the states of matter and the stages of transition between them. You definitely probably know about gas, liquid, and solid. Maybe you even know about plasma or supercondensates, but you probably definitely learn about the main three. And when you did, you probably use water as an example to learn them. You think about water vapor, liquid water, and ice as the three different states, right? Now, the interesting thing about that is that ironically, water is a bad example of the way that matter acts at the different stages, because water does funky things when it comes to the states of matter. Because when I think of a gas, I think of a state of matter that has a high amount of kinetic energy, which means the molecules are moving very, very fast. There's very little attraction between the molecules, meaning it's going to expand a lot, and it's not going to really hold its shape or its volume very well. When you cool it down, when you lose kinetic energy, then you get to a liquid state. Now, the liquid state is going to be moving a little less, and there's going to be a little more attraction between the molecules, which means liquids can hold their volume, but they won't really hold their shape. They will take the shape of whatever they're in. Meanwhile, if you put look at the solids have the molecules with less kinetic energy even. They're barely moving. They're like vibrating in place. They're going to have a lot of attraction between the molecules, and they're going to tend to be more dense, packed together. And, of course, this means it's going to hold its volume and its shape. So, of course, it's clear that these states of matter have everything to do with the amount of kinetic energy or heat or the temperature of the substance. It also has a little bit to do with pressure, and we'll talk more about that later in this video. But the point that you can use water as an example of this is funny, because what we learn about in biology is that water actually breaks one of the most basic rules I just talked about. Which one of these you think, for example, is representing the molecular structure of water in its solid state? Now, because I just said that solids tend to be more dense, you probably may have guessed that the one in the left side is going to be the solid state. But that's actually wrong. Water in the solid state looks more like the way it looks on the right side than on the left side. That means that water is less dense as a solid than as a liquid. In other words, when water freezes, it expands. And that is what I'm talking about when I'm saying it's not a good example of the way that most matter acts in the different states of matter. So let's see why that happens. It has everything to do with those hydrogen bonds that we talked about in the previous video of this lecture series. And of course, in gaseous state, you're going to have no attraction, so it's going to be the most expensive one. When you get to water, it's going to become a little more dense because, now the molecules are going to be a little more attracted to each other, the liquid water. Now, when it comes to ice, when the water starts to cool down, when it gets to about 4 degrees Celsius, the hydrogen bonds will lock in place and form this hexagonal crystal-like structure that you see on the left side. We call it a crystal lattice. Because the hydrogen bonds will lock in place, the molecules of water will actually be further apart in the ice than they will be in the liquid water, where the molecules are breaking and forming those hydrogen bonds all of the time, and that allows them to be closer together. But when they crystallize in the ice, it actually expands. This will start happening around 4 degrees Celsius, meaning the water will be its densest around 4 degrees. Below 4 degrees, the water will start to expand until it expands at its most when it finalizes the crystal at around 0 degrees Celsius when it's completely frozen. This is, of course, at sea level pressure. But what it's talking about here, and this is fundamental, and we're going to talk about why this is important for life later, water expands when it solidifies and it's less dense as a solid. Now, when it comes to the states of matter, let's see what's actually going on here. We're looking at the water as an example. Of course, what we talked about is the case. The gaseous state has more kinetic energy, liquid has less, and solid has even less. Now, what that means is that what's happening at the states of energy is that energy is being released or absorbed. Of course, remember the names of the state changes. When you go from solid to liquid, you call it melting. The other way around, you call it freezing. From liquid to gas, you call it vaporization or evaporation. And the backwards is called condensation. A word about evaporation, by the way. Evaporation can occur even if the water is not at 100 degrees. And we'll talk more about that in a second, all right? Then you have the water going from solid directly to gas, and that is possible if it absorbs enough energy, and that's called sublimation. And the opposite is also true, and it's called deposition. All right. Sometimes it's referred to sublimation as well, but I think that's confusing. So just call it deposition. Now, what's happening to the water molecules, of course, in the gaseous state, there's no attraction. In the liquid state, there's more attraction. And in a solid state, there's a lot of attraction, and the bonds of the hydrogen bonds actually locked in place, and the water forms a crystal. Another thing that's important to know is that wherever you go from solid more towards gas, you are absorbing energy. All right, so ice to liquid water, and then liquid water to gas, or from ice straight to vapor, all of these state changes are going to be absorbing energy. What that means is that you're going to make the molecules start to be less attracted to each other and break the connections between them. Now, the interesting thing about water is that before you can actually make that happen, you have to break the hydrogen bonds that link the molecules of water. Meaning, before water can heat up, you got to first break the hydrogen bonds that are inside it. This means that it takes a lot of energy to make water heat up when compared to other compounds. Meaning water is a good insulator, a good temperature regulator. It doesn't like to change temperature because it takes a lot of energy to actually break those hydrogen bonds that connect the highly polar water molecules to each other. And that's going to be important. Another thing that's important is that when the opposite happens, when you go from gas to liquid, or from liquid to solid, or from gas directly to solid, you're going from a state of high kinetic energy to lower kinetic energy. Meaning you're going to, in this case, release energy. Now, this energy is being released from what? Whenever the hydrogen bonds form, you actually release energy because less kinetic energy is going to be happening because the molecules are going to be moving less because they're now locked in a hydrogen bond, so you release the energy. This means that when something condensates, for example, so when condensation takes place, energy is released. And this is going to be very important too when we talk about the properties of water helping life. Now, another thing that's important to understand about all these things is that temperature is not the only thing that matters when it comes to state changes. Pressure matters too. In fact, it's possible to make something become vapor without ever heating it up. All you have to do is take away pressure. Because let's think about this. When you add pressure, you're pressing the molecules closer together. So you make them more solid-like. But when you take away pressure, you allow the molecules to expand, the opposite, and then they become more vapor-like. Now, if you actually get some liquid water, put it in a vacuum changer and suck all the air out, it will evaporate. And that's because there is no pressure holding that liquid together. Now, this is why when you go to outer space, you're not going to find liquid water, because all the liquid water is going to evaporate because there's no pressure in outer space. Now, this means that you can make something change state without just changing the temperature. Pressure matters too. So when you're talking about boiling point and melting point and things like that, it has to do with a certain pressure. In the case of water, water will freeze or melt around 0 degrees if it's at sea level, and it will evaporate or condensate around 100 degrees centigrade at sea level. Now, of course, if you add or remove pressure, you're going to affect that, and we'll talk about that in a second. But this takes us to what is called a state change or a phase change. Now, phase changes is the process of a substance changing state. Now, what's interesting about this, and you may not actually have ever seen this taking place, and we'll look at that in class, is that while the substance is changing state, it will remain at the same temperature. That means the whole block of ice has to melt before the liquid turns from 0 to 1 degree Celsius. The same thing is true when water is evaporating. The whole water has to boil and it become a vapor before the liquid goes beyond 100 degrees. So while water is boiling, it will never exceed 100 degrees. That's funny. So you put the water as an ice, you let it melt, the whole thing will stay at 0 until the whole ice is gone. Then we'll start picking up energy, and it will get to 100 degrees, and then, and only then, after the whole thing is gone, it will become hotter than that. So this is what we call phase changes. And this has something to do with the interactions that are occurring between the molecules. So in other words, the molecules which are still not hot enough to evaporate are going to be holding the temperature of the liquid at that minimal that is necessary for the liquid to evaporate. So that's what's going on there. Now, a little note about that. If you just leave a cup of water outside, it will evaporate by itself, even if you don't heat it up. What's going on there? Again, remember, pressure makes a difference too. So, and what's going on there is that even if it's one molecule at a time, molecules of water in that liquid can absorb heat and light from the air or from the atmosphere and then end up becoming hotter. But one molecule at a time, they will little by little evaporate and then go to the air. Now that's only going to happen if there's room in the air for the water molecule to be in it. If the air is already saturated with water, that's not going to really occur. So it has something to do with the vapor pressure or the amount of water that's already in the air. If the air is very humid, it's going to take forever for the water to evaporate. It might not even evaporate because that's why, for example, in Florida, when you put clothes to dry outside, it takes forever for them to dry because Florida is very humid. On the contrary, if you have a very dry atmosphere, evaporation will be very, very quick because there's a lot of room in the air for the water molecules to go to the air. So that means there's a difference between vaporization, which is when the entire liquid is boiling and becoming gas, and that's going to happen at 100 degrees Celsius, and simple evaporation, which can happen at any temperature when water absorbs heat. And this can even go from solid directly to gas by the same principle, and that's kind of how sublimation works. And then one last thing I want to talk about this too is that the whole thing about Celsius scale is actually set up based on this water properties, because we set up 0 degrees Celsius as the temperature that water freezes when it's at sea level, and we set up 100 degrees Celsius as the temperature that water evaporates or boils at sea level, and then we split the difference in 100 points. That is what classifies the Celsius scale. All right. Now, the last thing I want to talk about this is that since pressure will affect the boiling and the freezing and the melting and all that of water, if you go, say, to an area where there's less pressure, it's going to be easier, let's think about that, for water to evaporate. And it's also going to be harder for water to freeze because there's less pressure pressing, making water solid-like. This means that on top of a mountain, when there's less air pressure, the temperature necessary for water to freeze is actually below 0 because it's harder for water to freeze. Meaning when you see those ice glaciers on top of the mountains, in order for that to happen, it has to be even colder than 0 degrees. Likewise, on top of a mountain, it's easier for water to evaporate because there's not as much pressure holding the liquid as a liquid. Meaning the water will boil below 100 degrees Celsius, maybe 96, maybe 93, depending on how many pressures in the air. Now, that means that if you try to cook an egg on top of a mountain, it will take longer for the egg to cook because the water that's boiling is not boiling as hot. So the egg will take longer to cook. The opposite is true when you use a pressure cooker. When you put the water inside of a pan, and you close the lid of that pan and you're cooking under pressure, you're adding pressure on the liquid, which makes it harder for the liquid to evaporate. Meaning it's going to actually boil only at a higher temperature. So now the boiling point becomes 106, 107. Meaning that whatever food is there is going to cook faster because it's cooking hotter. So that's how pressure cookers work. And that's why an egg takes longer to cook on top of a mountain. And that is water and its physical states and everything you need to know about it. All right? So I'll see you in the next video where we're going to talk about the actual extraordinary properties of water. I'll see you then.